All right, good afternoon, everybody. We are going to continue our lectures on the topic of fluids. So, in the last lecture, we were here, right? We have just derived the so-called equation for hydrostatic equilibrium. Now, this equation has a name. It's called hydrostatic equilibrium. It just describes how the pressure of a fluid will vary. Okay, the pressure and also the density of the fluid will vary, and how they relate to each other when it's acted upon by the gravity. So under gravity, you will expect more gases, or the higher density of gases to be at the lower position, and a smaller density and smaller pressure to be at a high position. So this equation exactly describes that. Okay, so that is the meaning of this equation. And in deriving that, we noticed we use the balancing of the weights of the gas of the fluid by the difference in pressure. We imagine a small cylinder. Okay, a small cylinder. A small cylinder has a certain weight because of the fluid. So the weight of the fluid has to be balanced by the pressure acting on it. But it is acted by an upward and a downward pressure. An upward pressure from the top of the cylinder and a upward pressure from the bottom of the cylinder and a downward pressure from the top of the cylinder. But it happens that the downward pressure, the upward pressure is slightly larger than the downward pressure. So it supports the weight of that cylinder. And so that describes the change in pressure over the heights by this equation. Okay. Now, we made, for simplicity, we may assume a certain model of the density. How the density varies of heights, we may be given a certain model. Okay, and for simplicity of discussion, we assume a very simplified model of the density varies exponentially decaying with heights. So you can see this in this model, the density at Ez equal to 0 is equal to rho naught, and at when I go up with a larger Ez, then the density decay exponentially with this exponential factor e to the power minus az over h. And h obviously carries a dimension of a length, and this is usually called scale height. Okay, so there are typical heights. You can regard the typical heights in which the density varies very significantly over the heights. Okay. Now we substitute this density variation into the hydrostatic equilibrium equation, and we do the integration. Now, so the equation is given by dp dz equal to minus the constant rho naught g multiplied by this exponential factor. So we integrate both sides. When I integrate both sides, I integrate from a height of Ez, okay, a certain height, up to infinity. Now, suppose we are describing about the Earth atmosphere, and we can regard Ez equal to 0 at the sea level. And if I go to Ez equal to infinity, that means I go to outer space. Okay, in outer space, I don't have any air, so the density there will be 0. So when I go to infinity, Ez equal to infinity, I essentially goes to space where there's no air. Okay, so that's why I integrate from a certain height above the sea level to infinity. Okay, now so when I integrate this from Ez to infinity, I got P infinity minus Pz. But P infinity is 0 because I do not have air at very high altitudes. So I got minus Pz. Okay, and on the right hand side, I simply integrate this exponential factor again from z to infinity. And when I integrate this, it just gives me a factor of minus h. Okay, because when I integrate it, it just gives me this factor, this constant factor. And the minus h factor, the minus sign cancel with the minus sign in front. So I get plus rho naught GH. And exponential factor evaluate at infinity and EZ. When it's evaluate at infinity, the exponential factor is of course 0. So eventually I get the exponential factor itself with a minus sign. That is the lower limit, okay? Now, so what I get is that the pressure varies with heights, again, with the same exponential factor, okay? But the density, the pressure at sea level is given by rho naught GH, okay? So I find the pressure, the corresponding expression for the pressure. Now, what does the integration means actually? Like if you multiply this equation, both sides by A, the pressure multiplied by the area, you imagine a cylindrical area, okay, extending from the height EZ to infinity, okay. You imagine now you have a cylindrical, you have a cylinder of air, of area A, extending from EZ up to infinity. Then PA will be the pressure, right? PA with PEZA will be the pressure at the base, right? The pressure passing on the cylinder of gas from the base, okay? And the area multiplied by rho G, and also if I integrate it, it multiplied by H. If I integrate it with Z in this way, I am calculating the total mass of air. Okay. Now, if I multiply rho A by, if I multiply the density by the area, and I integrate the area, integrate the density along EZ, what I calculate is the total mass of air of the column extending from Z to infinity. So this equation essentially says that the pressure force from the base of the cylinder, it actually balances the total weight of air above that height, okay? So it's a balancing of the gravity force by the pressure, okay? Now, atmospheric pressure is huge, okay? It's very large, actually. And we are constantly under the pressure of the atmosphere, although we do not notice it because our body has accustomed to all this pressure. And also the inside of our body is also filled with air, and we also have atmospheric pressure inside. So there's a balancing of force from inside our body from the outside. Okay. Now the atmospheric pressure is typically of this order, about 10 to the power 5 Pascal. Okay. Now there's an easy way to understand it. That I mean to have a feeling of how large it is. Okay. Now imagine 1 meter square is actually 10 to the power 4 cm square, right? And 1 kilogram of weights is, by Newton's second law, is 9.81 Newton, is about 10 Newton, right? So imagine 10 to the power 5, imagine a meter square of area. You have 10 to the power 5 Newton acting on it due to the atmospheric pressure. But 10 to the power 5 Newton is 10 to the power 4. 10 to the power 5 Newton is 10 to the power 4 kilogram of weights, equivalent kilogram of weights, right? So 10 to the power 4 kilogram of weights, if I divide it to 10 to the power 4 cm square, it means 1 kilogram of weight per cm square. So it's easy to understand how large atmospheric pressure is. If you have 1 centimeter square of area, the atmosphere acts on this area with a force equal to the weight of a 1 kilogram object. Okay, is that clear? So 1 kilogram of weight acts on 1 centimeter square of area. Okay, so imagine you have a plastic sucker. I can pull on this plastic sucker, and it requires a large force to pull it apart. Okay, because inside between the plastic sucker is almost a vacuum, so the atmospheric pressure press on the sucker, and so that's very difficult for me to put it apart. Okay, now how large can the force? How large is that force? I can have a rough estimation. If I assume that for simplicity, the plastic sucker has 4 cm in radius. Okay, it has it's circular and is 4 cm in radius, and that will produce an area of pi 4 square. Pi 4 squares would be the area, and if I assume 1 kilogram of weights per cm square, I will get 50 kilogram of weight about per cm. 15 kilogram of weight. No, sorry, this is wrong. Not per cm square, but in total. Okay, totally, I will have 50 kilogram of weights pressing on it. But of course, this will not be the actual force required to put apart. The actual force is actually less. It's about 1/2 of it at most. Okay, because inside there, between the two sucker, is not completely vacuum. There are still some air inside, and so the pressure from the outside will not be the exactly pressing on the vacuum. Okay, so the force will be less than the maximum value. Sorry for the typo. Please cross out the per cm square here. Okay. Now we also would like to discuss about the so-called Pascal principle. What is that? Now, if you have a fluid, imagine you now have a balloon. Okay. Suppose you press on the balloon from one side. You press on the balloon from one side. You will feel that the balloon, the pressure on the balloon increase because you press on it. And that change in pressure is undiminishedly transmitted to every part of the balloon, not just the part you press on it, but to every part of the balloon that you may be feeling. Okay, you will feel that the whole balloon is under pressure. Now that's Pascal's principle. Pascal's principle says that a change in pressure applied to an incompressible fluid is transmitted undiminishedly to every point on the fluid and to the container wall. Now, of course, a balloon is not a very good example because air is actually compressible. Okay, so maybe that is not a perfect example, but you actually feel the pressure to be transmitted from one side of the balloon to the other side, to all the parts of the balloons, right? And if you consider water is a fluid which is almost incompressible. Then the pressure will be transmitted undiminishedly. That means that is without lowering to every part of the fluid. Okay. Now, so this is an example. Suppose you have a fluid here, which is incompressible, and you now have a piston. Suppose this piston is light weights, so you don't have to consider weights. But there's a lead salt pressing on it. Okay. So there's a change in pressure, right? I want to know what is the change in pressure at a point P, which is at a certain height above the liquid surface. Okay, I assume the height to be h. Now the pressure is due to two parts. The first part, because my point here is at the heights h below the liquid surface, so there will be a pressure due to the hydrostatic force, and that is rho gh. That is due to the weight of the liquid. Okay, when you are at a height h above below the liquid surface, you feel a pressure of rho gh. That is the first part. And the second part is due to the lead slot, maybe the piston or the lead slot, all together. So this is external pressure due to the weights of the lead slot and also the piston. Okay. Now, if I add more lead slot to this container, the weight will increase. So I will exert a greater pressure on it. So the changes will be transmitted to all parts of the liquid. So immediately, when I add the lead slot, I will feel, if I'm a creature here, I will feel the pressure increase immediately. Okay, and the pressure change is just the same as the external pressure change. Delta P at this position is equal to delta P external. Okay, assuming the liquid to be incompressible, so H doesn't change, the fluid pressure doesn't change. Okay. Now, the Pascal principle has an interesting application known as a hydraulic lever. A hydraulic lever is a lever that makes use of the pressure of a liquid, for example, oil, to lift up a heavy object. Okay, so it is a lever. The lever is something that is a machine used to lift up a heavy object. Okay, now consider this container. This container consists of two cylindrical volume. This cylindrical volume has a small opening. The area is small. I denote this area by A1. And there's a piston here for me to apply the force. The applied force is Fi. So the force, the input force is applied here, and it's called Fi. And the area of the piston here is Ai. Okay. On the other side, I put the heavy object. This other side has a much larger cross-sectional area, which I denote by A0. And the output force, I denote it by F0. Okay, so the input force is denoted by Fi, the output force is denoted by F0. Okay, and now we are going to find the relationship between the two. Now, since the pressure, the change in pressure will be the same on both sides, is that right? So that means delta P is equal to Fi over Ai and is equal to F0 over A0. Okay, if I apply the pressure here, that pressure change will be immediately felt on the other side. Okay. Now, if they have the same level, originally the force are balanced. Okay, because the liquid are in the same level on both sides. But when I apply pressure on the input side, that pressure will be transmitted to the output side. Okay, by this relationship. Okay. Now, so I can solve for the output force. Output force is equal to A0 over Ai Fi. But since A0, the output surface area is much larger than the input surface area Ai, A0 is much larger than Ai. From this equation, you can immediately see that F0 is actually much larger than Fi. So I can use a small input force to deliver a large output force, such that it can be used to lift a heavy objects. For example, a car. Okay. Now, but you have to pay. You have to have a trade-off. Although you can deliver large force, but the energy has to be conserved, right? The input energy has to be equal to output energy. So there must be some trade-off in it. How do I calculate that? I calculate that by using the work done. If I press on this piston, and the piston is lower by height of di, I suppose di is much more than the level of the oil. If the piston moves downward by a distance of Ai, the work done, the input work done is what? The input work done is Fidi, right? And the output work done here, now the piston here will move upward, right? And I assume it to move upward by a distance d0. So the output work done will be F0 d0. Okay, but I have assumed that the oil here is incompressible because I'm using the Pascal principle. So that the volume decrease on this side must be equal to the volume increase on the other side. So that means the area multiplied by the displacement should be equal. So A0 d0 is equal to Ai di. Is that right? That is the conservation of volume if the fluid is incompressible. The area multiplied by the distance moved by the piston, that volume must conserve. If I press it down on this side, the same volume must go up on the other side. Okay. Now let me apply this equation to here. Okay. Now because I know that the forces are related like this. Okay. So that means if I apply this relation, I can easily verify that the work done input by my applied force is just equal to the work done output on the other side. So the total energy is conserved. Okay, I don't assume any loss of energy here. But you can see, since my applied force is small here, I have to move a large distance in order for the piston on the right-hand side to just move a little bit. So that is a trade-off. I have to move a large distance in order to lift the object just by a little bit. Okay, that is dictated by the conservation of energy. Okay. Now this is a schematic diagram of a hydraulic press. It actually works like this. Okay, and this is a real thing used to lift up a car. Okay, so I deliver a much larger force but move over a much more distance. Now then we will discuss about so-called Archimedes principle. Now Archimedes principle is concerned with the buoyancy force or upwards. 浮力, okay? The upwards is the upward force exerted on the immersed body due to the difference in fluid pressure. When I have a body immersed in a fluid, like for example, water or air, the body will be exerted by the upwards force. And upwards is simply due to the difference in the liquid pressure on different parts of the body. Now the upwards is not a separate force of nature. It's not a real new force. It is just generated by the fluid pressure, by the uneven fluid pressure from different parts of the body. Now, how does it come about? Suppose this is an object. Okay, this is an object of volume V. Now the object is immersed in, say, water. Now at the base of the object is at a larger depth, okay, from the liquid surface. So since it's deeper, the pressure force exerted on the lower part will be larger. At the upper side, for the upper surface, the upper surface is closer to the liquid surface. So the pressure force exerted on the upper surface is less. So there will be a difference in fluid pressure. The fluid pressure at the base is larger than the fluid pressure at the top. So there will be a net upward force from the fluid acting by the fluid on the object, and that is the upwards. Okay. Now Archimedes' principle says that the buoyancy force produced by fluid on an immersed object is equal to the weights of fluid displaced by the body. Okay. How do I understand this? If you have a body totally immersed in the liquid, for example, the fluid dissipated by this body will be exactly equal to the volume of this body, right? So I can use the volume of this body, multiply by the density of the fluid, and multiply by G. Now, with a volume multiplied by density, I get the mass of fluid. Now, this is the volume of fluid displaced, but not the volume of and in this case, it's equal to the volume of the object. Okay. When I use this volume multiplied by density, I get the mass of the fluid displaced. And when it multiplied by G, I get the weight of the fluid displaced. And this is the upward force. Okay. Now I can show you a better picture of this. Suppose now I have a balance weighting in object in air. And in air, of course, the weights, the true weight of the object mg is a reading of the balance, right? So the balance reads mg. Suppose now I immerse it in water. I immerse the object totally in water. And suppose now I have the liquid level of this container full, so that when I put this object into water, the liquid is displaced out. So I have another container collecting the displaced liquid. And the amount of the volume of liquid displaced in this example is exactly equal to the volume of this object. Okay, so when I have the object immersed in water, the weights of the balance, the weight measured by the balance, the apparent weights measured by the balance, will be equal to mg, the downward force, minus the force due to the upwards. Because the liquid exerts a force, the upward force on the body, and that makes the body weight less. Okay, so it's equal to mg minus fb. But fb is equal to the density of the fluid multiplied by the volume displaced, and in this case is equal to the volume of the object multiplied by g. Okay, so that is the upward force. So the body weights apparently weighs less when immersed. And this relation is actually true when the body is either totally immersed, just like this figure, or partially immersed. Now, if the body is partially immersed, then the volume of liquid displaced is not equal to the total volume of the object. It is only equal to the part, the volume of the body that is immersed, but not the total volume of the body. Okay, can you see the difference? But if you use that displaced volume to calculate upwards, the law of Archimedes still hold. Okay. Now, so this is what happens when a body is totally immersed in the liquid. The net force acting on the body is the weights minus the upwards. I choose the downward direction as positive. And since the body is now totally immersed, so mg, the weight of the object, is the density of the object, rho s, multiplied by the volume, multiplied by g. This is the weight of the object. And the upwards is the weight of liquid displaced. But the volume of liquid displaced is just the same as the object itself, right? So the weight of liquid displaced is rho Vg, where rho is the density of the fluid. Okay. So now I have, after taking out vector Vg, I have rho s minus rho g Vg. Now you can see from this equation that if I have rho s larger than rho, if the density of the body is larger than the density of the fluid, then the net force will be what? Will be in what direction? Will be in the downward direction. I take downward as positive, right? If it's in the downward direction, that means the body will sink. Okay, will sink, and that is commonly observed. That is what you learn in high school curriculum, right? If the average density of the body is larger than the density of water, then the body will sink in water. How about if rho s is smaller than rho? If the density of the object is less than that of water, then this will become negative. And that means the net force is upward. And so the body will flow inside water. Okay. So these are the observations you have in high school, in your junior science curriculum. Now we express it more precisely in terms of Archimedes principle. Okay. Now here we present a proof of Archimedes principle. Now we are a little bit more ambitious. We consider an arbitrary shaped object. Now we know that somehow the horizontal force due to pressure acting on this object must be balanced. The only unbalanced force is the vertical force. Okay, the vertical force due to the pressure is unbalanced. So we now divide the object into a lot of small vertical strips. You imagine a very thin vertical strip composing the body. Okay. Now, suppose we take out one of the strip. The strip has a height h here, and it has an upper surface and a lower surface exposed to the liquid. So we take out this strip. The upper surface is inclined, the lower surface is also inclined, but they may incline at different angle. I assume that the upper surface inclined at the angle alpha 2, the lower surface inclined at angle alpha 1. The upper area is A2, the lower area A1. Okay, that is our my notation. Now we assume the cross-sectional area of this strip to be A0 delta. There should be a delta here because it's a small area. Okay. Now, what is the pressure difference between the upper surface and the lower surface? If the pressure at the upper surface is P, now this P already include whatever pressure. It includes the fluid pressure there. It also may also include the atmospheric pressure. It is just the pressure of fluid pressing on the object at the top of the strip. Okay. So the pressure force, the total pressure force will be that P delta A2. Is that right? Now, but if the pressure at the top is P, the pressure at the bottom must be P plus rho GH, since the bottom is at the height H below the top, right? The bottom cap is at the height H vertically below the top cap. So it must have a additional fluid pressure of rho GH. So that is the pressure at the bottom, right? So the pressure at the bottom is P plus rho GH multiplied by delta A1. Okay, now but the pressure force act on a different direction, right? So in order to find the vertical force, I have to multiply a cosine factor. At the base, we multiply cosine alpha 1 to get the vertical component. And at the top, we multiply the PA2 delta A2 by the cosine factor cosine alpha 2 to again get the vertical force. Downward, for the upward force, we have a positive sign. For the downward force, we have a negative sign. So, so the difference between these two terms will give me the net force acting on this water column due to the pressure. Okay. Now, but you can easily see from this right angle triangle that delta A1 cosine alpha 1 is just delta A0. Delta A2, again, cosine alpha 2 is just delta A0. It's also delta A0. So this factor are just common. They are equal. The two delta multiplied by the respective cosine, they are the same. They are both equal to the cross-sectional area of the column. So I replace it by delta A0. I replace them by delta A0, and I take this factor out, and I can see the pressure P cancel, and I have the result as rho GH multiplied by delta A0. But H multiplied by delta A0 is essentially the volume of the solid column, right? This is the heights multiplied by the cross-sectional area is the volume of the solid column. Now this two triangle is very small when the volume of this triangle is sufficiently small. If I let the area of the column to tend to 0, so I can ignore it when I have a sufficiently large number of column and the cross-sectional area of each column is sufficiently small. Okay, so if I form a summation of all this, okay, this is the pressure force acting on one column. There's another pressure force acting on another column. So when I sum over all the column, I just get the total volume of the object, right? So I get from a sum of all H delta A0, I get the total volume of the solid. Okay, and in this case, because I assume the object to be totally immersed, the volume of the whole body is just the same as the volume of liquid space. Okay, and so I get the efforts as rho Vg. So I proved the Archimedes principle. Okay. Now, what happens if the volume is not totally immersed? Suppose the body is not totally immersed, but partially immersed. Now, I can apply the same argument. I pick out a column of material, a column of the body, a thin column of that. The pressure at the top is atmospheric pressure. Okay, I call P naught. The top part is now not in water, it's now no longer in water. So the only pressure here is the atmospheric pressure, I call P naught. The pressure at the base of the column is the atmospheric pressure plus the hydrostatic pressure. The hydrostatic pressure is rho GH. Rho GH is not the total height of the column, but the height of the part that is immersed in water, and that is this height. Is that right? Because it's only the depth of water can produce the pressure. So I count only the depth of water. And this is exactly the heights of the liquid column that is immersed in water. Okay? So the pressure here is rho P naught plus rho GH. Now let us follow the same argument as before. We do all the same thing here as before. And eventually we sum up all the summation. We form a summation of H delta or A naught over all the columns. So, and eventually we get the upwards force as rho V prime G, where V prime is now no longer the total volume of the body, but the part of the volume that is immersed in water. Okay, and so that's why we call this volume V prime. So for either total immersion or partial immersion, the upwards force, the upwards or the buoyancy force is always equal to the weight of liquid displaced by the object. Okay. And V prime here, I denote this part, the volume displaced by the object. This is equal to the volume of the object immersed. Okay. Now this is an iceberg. Okay, this is not real. It's a drawing only, but it shows to you that actually the iceberg is very large, and most of the icebergs is actually immersed in water. You cannot see it. Only a small part of the iceberg is above water. That is a small part you can see above water, but it actually there's a large part, a much larger part, which is underwater. Okay, so that is why the Titanic tragedy happens some 100 years ago, when the Titanic sailed to a very cold region. The sailor at night, they cannot see very clearly at night. So when the ship is getting close to a giant iceberg, the sailor just managed to discover a small iceberg just above the water surface. But there's a gigantic iceberg below the water surface, so that eventually the sailor is not responding fast enough. So the ship collide with the giant iceberg and eventually sank. Okay, so that's why there's a tragedy. Nowadays we have a more advanced instrument like radar. We can use radar to detect the part of the iceberg below the water surface. Now let's understand using Archimedes' principle why most part of the iceberg cannot be seen above the water surface. Now the density of seawater is 1025 kilogram per meter cube, and the density of ice is 917 kilogram per meter cube. Now you notice that the density of ice is slightly smaller than the density of pure water, which is 1000 kilogram per meter cube. So that's why ice can float on water. Okay, the density of ice is actually less than that of water. And the reason is that when water forms ice, the hydrogen bond actually become rigid and it forms a crystal. And the solid actually is expanding. Expand by about 8% compared with the liquid counterpart. So when the water become ice, the whole thing expands by 8%. So the density get less than decrease by about the same percentage. Now, for the balancing force, the weight is equal to F first. The weight of the iceberg is equal to rho SVG, right? This is the volume of the whole iceberg. But the F first is equal to the density of water, that is seawater, multiplied by the volume of water displaced. That is the volume of iceberg immersed, okay? V prime multiplied by G. So that means V prime over V is rho S over rho. And the density ratio, when I put in these two numbers, I get 0.985, which is about 0.9. So that means only 10% of the iceberg is above water. Okay, one tenth of the iceberg is above water. The rest of 90% is below water. Now, if I classify for you, suppose you have an object. For simplicity, I assume the object to have a uniform cross-sectional area of A, and the height of the object is H. The object is somehow at rest, found at rest between the interface of water and oil, okay? Oil has a smaller density than water, so it flows on the top of water. So the density of oil is rho naught, the density of water is rho W, but somehow this object has a density between oil and water. So it's suspended, okay, at the interface of the two liquid layer. And I now would like you to calculate the height x of the object that is immersed in water. Okay, if I assume the density of the object to be rho. Okay, so you apply Archimedes principle, but you have to apply it using two layers. The first layer is the upper layer. The upper is from oil. The lower layer is the upper is from water. And if you take it into account these two uppers, the total uppers is equal to the weight of the object. Okay, so you take 4 minutes to do it. You just write down the correct equation. So have you got the basic equation? Okay, let's do it together. Any of you have got the answer or the basic equation? Now let's do it together. Now you have a height x that is below water. You have a total height h of the object. The area is A, the density is rho. Oil has density rho naught. Water has density rho W. So what is the upwards on this part? The upwards on this part will be equal to rho naught, because this part is in oil. This part has a height h minus x, right? The height multiplied by the area will give you the volume, and the volume multiplied by density of oil multiplied by G will give you the weight of all this space, and that is the upwards. So the upwards on this part is given by this. The upwards on the lower part is from water. So you have rho W x, right? X is the height multiplied by area A. This is the volume. This is the weight of water displaced if I multiply by G. And that is, of course, equal to the total weight of the object. The two upwards added together is equal to the total weight of the object rho A H G. Is that right? So that all the G cancel on both sides, right? And now I have such the A and the G, they cancel. So now I have rho naught x minus h plus rho W x equal to rho h. Is that right? Now I can solve for x. X rho W minus rho naught. I can put this term on the right-hand side. So it becomes rho minus rho naught. The first time I can put it on the right-hand side. So it becomes rho minus rho naught h. So now I can solve for x is equal to rho minus rho naught divided by rho W minus rho naught h. This is the answer. Now I have a check over the answer. I know that rho W must be larger than rho naught. So this must be equal to 0, right? And the density of the object must somehow be larger than the density of oil, right? Otherwise, it will not sink in oil. Otherwise, the whole object will be floating in oil. So the density of the object must be larger than the density of oil. So rho must be larger than rho naught. So this quantity as a whole must be larger than 0. So that means x. Okay, I have a positive x. That is solvable from this equation. Okay. Now, so let's have a break of 10 minutes. Okay, if you have a question for me, please ask. And after 10 minutes, we will come back to discuss about fluid motion. We'll discuss a balloonist equation, which is the ideal fluid motion. I share the screen with you first. Okay. Now I might have to arrange a makeup class, just one class maybe, I think I'm behind the schedule about around one double lesson, so I may have to arrange a makeup class after the break of the semester. Okay, and also I urge you to arrange to form groups of 2 students. I think the TA they have already formed groups with some of you, right? But if two happens to not attending the exercise class last Monday, you may like to form groups for yourself. Okay, if I do not hear from you early next week on next Tuesday, if I do not hear from you uh, by next Tuesday, I will form a group arbitrary with you. Okay, but you can still use the information provided in the blackboard to contact your group mate. So you together will work on the project, which will be released to you next week. Okay, I will release the project to you in a reading week, so you will have sufficient time to do it. Okay, you have about 3 weeks to do it before you do the presentation in the last exercise class. Sorry, I will not let you. I will not let you choose the topics. I will arbitrarily assign it for you. Since I just put your name in alphabetical order, your groups in alphabetical order, and then I arbitrarily assign the project for you because you have too many groups and I cannot cater for you all of your choice. So I have to assign it arbitrarily for you. Oh, sorry.